I really don't post a lot of things to YouTube.
You post any?
Nah, not really. I just watch a lot of videos on YouTube.
All right, questions? Guys, let's husband the time. Questions? Anyone? Yes, please, Joy.
I just have like a syllabus question. I
Okay.
noticed today that there was problems written at the end of each. Is that like just for practice at home, or you're collecting those? Like,
Wait a minute.
I thought I saw.
What you talking about?
Hold on, let me just check. Oh, these are just the page numbers, not problem numbers.
All right.
So then when do you assign a problem set?
Problem set, I'll assign a good time before the midterm
Okay.
and before the final respectively. So that you hand it in, I then correct it, give you the feedback, you have the time to digest it and do well in the test. It gives you an idea of the test, but I also assign problems as we go, right?
Right,
You
yeah.
had some warm-up exercises last time and such, right? But the problems will be assigned, as a sort of
Practice for the test.
practice for the
Okay.
test as well put, well said. Okay, any other questions? Okay? All right, yes, please.
On the homework you assigned,
Yeah.
when you said a couple of numbers you gave had a negative sign, did you want the two's complement of it?
No, I didn't want two's complement of it.
Okay.
I don't want to get mired in two's complement in this class. It will come up here, right? But we don't have it in the time budget. It's a nice, you have to know it, but likely I'm not responsible for your knowing it. And it will only come up in the context, as you will see today, of the range of values, right? So I will not ask you in the test to convert anything to or from two's complement.
Okay.
Right? It's what you should know. It's simply that I don't teach it because otherwise we'll get bugged out. Right? We'll stop. And we can't afford it. Okay, so Stephen put up some numbers for us, some conversions, whatever we want to put up since he brought it up. And any questions, while he's putting up anything so that he knows that I well. I want to have a high energy class, it wakes me up, it wakes you up. That's important. I speak a lot internationally, and I've noticed that, long time ago, that you have to pump energy into the road. That's the most important thing, and then people sort of, pile on to the energy. Otherwise, if you drill off, and that is a lesson to you when you present something. It's very important, because then people listen. Otherwise,
Yeah.
and then I would drop off. That's the going Very important. Want to talk?
No, there's probably.
Oh, okay. All right.
I just left.
Okay, I thought you did all the work. All right, no, this is too big. I didn't ask you.
Oh, there's a decimal point in there.
Decimal point in there
Yeah,
somewhere,
sorry
right?
about that.
Okay. Again, it's not a torture chamber, You just have to know how to do it. Okay, it's going over here. Okay, so why don't you convert something? Let's say take those two numbers and convert them. You can, whichever way you do it. I do it by inspection.
No, sir, in that question, would it be minus? Like for the binary, it would be positive only, right?
Would be what?
It should be positive for the binary.
That
question.
one?
Yeah, this question.
You mean the way I signed it?
Yeah.
I don't know, I just took it
that
off
one
the
was
top of
negative.
my head.
Yeah, that was negative. That's
That
what-
was
That was one was positive, I think one was
Yeah.
negative. But again, it doesn't matter.
It doesn't really.
It doesn't come into play. We leave it alone. We don't convert to those complements.
It's the same thing. It's going opposite directions.
Yeah. It's a warm-up, yeah? Easy, right?
Tell me have to.
What did you do? You did the low one?
I did two complement.
All right, good. Oh, you know, good for you. That's good. No, I don't want to get married into a couple. I don't want to get involved in things we don't need. You will see that in the floating point representation, we stay, in fact, away from Tuscan. I mean, that's the way the representation is. Because otherwise, the numbers are hard to compare for sort of larger and smaller, if the numbers are Tuscan.
Get that one wrong. Because I did the two's complement.
All right, whatever here, right? So that gives us what? That gives us 6, right? And this is 16, 32, 64, 96, 106, 112, 118. Good. Good. That you can do it by inspection. You can do it whichever way. I sort of look at what fits in. 96, right, meaning 64 and 32 fits in, and then what's left, right, is 4 and 18, 22, right? So that is what we have here, 16 and 6. Right, you will see it later. Okay, any questions about that? I don't want to waste too much time, but questions. I mean, I want everyone to, again, some people know more stuff, some people know less stuff, but I want everyone to be in the same place. You okay?
Yes.
Okay. You okay? Good, all right. And that is okay, right? Okay? What we have here is what? 8, 10, 11, right? This is 11 decimal. You have to be careful, right? And then this is 16, right? And there's no 32. And this is 64 and 128, right? Add it all up. Okay, good. Then, this is just a warm-up for you, the review. Any questions on that? Any way you were taught to do it, you do it. And then I asked you to get the addresses, right? Okay, Mona, you want to put it up? Okay.
I have a question.
Yeah, good.
You know,
What? Oh, yeah. Nice, thank you. Okay, then you give it. Yes.
When converting the decimal, well, the 0.875, it's the same, you do the same steps that you do for the 118.
No, well, the way you convert, actually, the procedure is different. You multiply. But I mean, again, I don't want to get mired into it. So in other words, it's like that for the needs of this course. Right? Right? One eight. Right? And then if you add them all up, right? If you add them all up, you get 0.1112. Okay, so that's all we need to know here. Because I'm trying to teach you other things, so I don't want to get like that. And this gives us a good opportunity to review it, so that you are comfortable with that, but we need other things, what we talked about before. Any questions about the address length and capacity? Address length, remember I proved it to you last time, is the log of capacity. In other words, it's the power to which you have to raise 2 to get the capacity. Right? And I gave you a little paper in the handout. K is 2 to the 10th, 1 so that, we won't be playing with large numbers. We will always express it as, let's say 2 to the 15th, right? Which is what? What? 32K, right? And so the address length is 15. log of that. Right, so if I'm asking you what is the address for that, right, you have to take log of that. Right, log 2 to the 15. 50. Okay? Okay, thank you. Okay. Okay, what have we here? Right. For 16 terabytes, right, tera is 2 to the 40th, and we have to add to it log of 16, which is 4, and that is 44 bits. Okay? And this is 2 to the 30th, this is 8, 38 bits. Right? Good, thank you. Any questions? Now, if you have questions, just pipe up. Don't save them for later. There's no late. I mean, you know, because otherwise we have to put it on the stack and then pop the stack, right?
And then dump it.
And then dump it. That would be bad. That's bad. What?
Court.
Enough of those metaphors, okay.
For the person who brought it, yeah.
What?
Not for the person who sold it.
So what? Who did what? Where are we now? What are we talking about?
I love the joke.
All right. Okay, guys. And then, of course, going back, you know, let's say it was, you know, 39 bits. You can address what?
$512 gigabytes.
Thank you very much. Very good. That's exactly it. Okay. So we're on top of that. If anyone has questions, last call. Okay, let's get on with the data types supported by modern architecture. Right? In other words, available on the hardware level, and we are talking about the superset. In other words, anything that can reasonably be offered aside from perhaps some display type data types. Okay? So we will start with the numerics. Okay, now, I'm talking about data type representations, of course. Remember, the data type is characterized by the representation, the set of values, you will see both, and then the operations. Right? Operations we'll discuss next, because that comes into the instruction set, where we have the data and the instruction sets. This is the data type. We'll start with the big one, Roman of numerics. Right? That's why I wanted you to warm up a little with all this good stuff. Okay. Then we have, of course, integers. Right, let's start with integers. Now, we have two kinds. You will tell me, why do we have two kinds? Why do we need them? It's a nice sign-up sheet. In other words, we have signed and unsigned integers. Okay? One byte. What is the range for signed with 1 byte? It ranges between 1, 0, 6, 8, 8, right? Because this is decimal. 2, what? decimal. Right? This is negative, that is positive. Those are signed numbers. That is a sign. What is the value of that? And that is 2's complement, to be honest.
Wouldn't the top number be 0? Wouldn't the first one, the first byte represents the sign.
This is the only byte. There's no first byte. This is 1 byte. We're talking 1 byte, then we'll generalize to a word of any length.
But the leftmost bit would be
The sign
sign
bit.
So
That's
wouldn't
the sign bit.
So wouldn't the one below that be the 0? Because isn't that negative negative?
Wait, this is negative. Right. Thank you very much. Very good. I make mistakes just on purpose to see what they are learn. All right. Very good. Very good. What? 0 is positive, 1 is negative. That's right, in 2's complement. What's the value of that? Minus 128. And that?
Positive 127.
100, what?
127.
Perfect. Okay, now there's a story to be told by that. I'm not just putting those two for their own sake, which is important, but there's a story that impinges on the floating point number representation. Okay. All right. In general, sign in and with word range is what? Minus 2 to the n minus 1, 2 plus 2 to the n minus 1 minus 1. Right? Thank you. Also, if you have any homework to, and then good. So I'll always give you feedback. I encourage you to handle it. Okay. Right? This is what? Minus 2 to the power of 7, which is the length of the byte is 8, minus 1, right? And this is 2 to the n minus 1 minus 1. You see that, right? If you don't see it, I'm in hollow. You're comfortable? All right. And then for the unsigned, now why do we want signed and unsigned?
Certain numbers are going to be signed and certain ones are going to be unsigned.
Well, this is true. Sometimes we want it for the correctness check. That's right, for the software, right? What, let's say, would be another reason to have, because presumably unsigned I included in the signed, but
We'll use a space of memory or addressable memory.
no, we still have 1 byte. The range, right? The upper range is larger, right? Let's see. The range here in the byte is what? For unsigned numbers. What's the range?
255?
What?
255?
Right, from 0 to 255. In other words, 0 to the power of n minus 1. Okay. Now let's look at unsigned, right, in n bit word. You have the range that is what? 0 to 2, right? This I've given it away to 2 to the n minus 1. Now, look carefully. And this is presumably what we have. Those are the ranges, 2 representations. I needed ones are ordinal numbers, right, that go on the up. Let's say like, addresses can go back and down, right? But we could have some counts and whatever that can be only positive. But the important point is,
What's the symbol that you use?
so, 0, so.
Okay, gotcha.
That's a so. Okay. Now look what happens. Okay. look at that, and then this. If we add 128 to each number here, and then we move all the numbers into the positive domain. Okay? You might say, what's the big deal? It's a nice observation, but what does it bias? Well, it biases the representation of the exponent in the floating point notation, where you have to compare the exponents. The exponents will be negative and positive, right? But we want to bias them so that they can be compared for smaller and greater. When you have one or two's a complement representation, the comparison is difficult, because simply the larger values are the ones that are zeros that are complemented to ones, right? So as you will see in a moment, this observation has been used to develop the floating point notation, right? Save it up, and it will come up now. Now, just to refresh your memory, why do we have complements all together as opposed to sign magnitude? It's nice to torture students, but other than that, what's the good of that? I mean, why not live simply and cleanly, you know? You have the value, you append the sign. Who needs complements? So you've been going to that temple all the time and you don't know why? Remember, the whole rationale of having complements is so that you can perform subtraction by doing addition. In other words, the numbers in complement representation can be subtracted with the same algorithm as addition, which again biases the same, similar algorithm for division as for multiplication. We don't have to take off, right? We shift in another direction, but we keep adding, right? So, in other words, we don't need the subtractor and we don't need the divider. It's very simple, right? Now, then we have two kinds of complements, two's complement and one's complement. One's complement is never mentioned anymore. There was Burr's architecture, which was very important, very elegant and very over-engineered, but it went by the wayside because it was using all kind of weird stuff. That was elegant at the time, but nobody wanted to live like that. It had a machine language that was algo. Now, if you think that C is hard, algo was very hard, right? I remember that language. So one way or another, one's complement has two representations of zero, positive zero and negative zero. And there's no good reason to have that, so we stay with two's complement. Okay, that's the last we want to know about two's complement. Let's talk about floating point. And why do we want floating point? What is floating point as opposed to whatever, right? So this comes into then floating point numbers. Okay, why do we want them? Again, the main thing is why. That's the main question, like Tosca. Because all of that rigmarole has to serve something.
Precision.
Well, precision is actually an issue.
To get more space or numbers.
To get the greater dynamic range. To get the greater dynamic range, which is in the plain language means that you can represent very small and very large numbers in the same variable, which happens, right? And you will see just how large and how small.
So it's kind of like scientific notation.
It is scientific, that's exactly right. Only scientific notation we apply to presumably the decimal, it is scientific notation, and so this is exactly right. Notation applied to the That's why we make some adjustments. Representation of the binary. Okay, so you remember scientific, and again, the book uses the fancy word significant, right? Which is again, that's the mantissa. I'll be using mantissa because you're probably used to that. Right, so we have the number plus or minus, right? Then mantissa times base to the plus or minus exponent. Base, some of you might know it as radix, and that's the exponent. Okay? Now, we need to store in a word, I'm using a 32 word for our purposes, we need to store in a word how many values, looking at that. And again, remember,
You need one for the sign.
we need the sign, right? And that is the sign. Right. And this is the sign of number. In other words, that's that sign. What else? Well, we need to,
8 bits.
what?
8 bits.
This one?
8 bits.
This one.
Yeah.
We'll be using, this is actually standard, we'll be using 7, 24, and 1. Because we'll be using the IBM mainframe representation rather than IEEE standard. You're right, in IEEE standard this is 8 bits. But then it gets a little more complicated. Because in the IEEE standard, the bias is 2 to the power n minus 1, plus you have a hidden 1. So in other words, there are some wrinkles. I will assign to you the IEEE standard for the homework side. So you will be able to have it, but for teaching, it becomes cumbersome. So I want it to be clean, and this is the IBM mainframe notation. Right, so if you use the text, if you use the textbook, remember they use IEEE standard. So don't look at it that way. They mention that, they show that, but they use IEEE standard, which makes seeing what's going on very difficult. All right, now here we have the exponent, and here you have the mantissa. Okay, what happened to the base?
It's always going to be 2.
Well, it's fixed. It can be 2 or 16, and we'll compare the two. The IEEE standard relies on the base of 2. You will see the trade-off. IBM mainframes rely on the base of 16. Yeah, and some reasons are paradoxical. What?
Doesn't IBM have it so they can have more memory address space?
It's not the question of the memory address space. You will see that the range is vastly larger, right? Because obviously, if you raise this,
you raise the base.
its exponent gets multiplied by 4 right away, multiply, if you have the base of 16. And the base is implicit. The base is built into the hardware. Actually, you don't need to store it. It's base of 2 or base of 16, and we'll compare the two. Okay? So, for example, let's say you have plus, I don't know, whatever have you here. We will be working with those things. But, if you remember your scientific notation, you might have something like that. I'm just showing you what it would have you here, just a number. Now, there are two things about that number. And you will see that you will have to internalize and be comfortable. This numbers normalized. In other words, the first digit, this is the first digit after the radix point is non-zero. Why do we do that?
Another zeros don't matter.
Because, no, well, they matter, but we don't want to store zeros. The zeros go into the exponent, right? We don't want to store zeros because this is a great value. Every bit here counts, right? And the other thing is this will be biased. And that is something I will show you here. Right, so let me write it down for you nicely. This we don't need anymore. This we need. And there are two facts about the floating point representation. You have to be comfortable with that, and you have to understand why we do it that way and how does it work. Okay, one, the mantissa is normalized. That's what I was just explaining. I am the first, well, I should say it's a fraction. It is a fraction with the leading non-zero digit. Right, like I showed it to you here in the decimal. Right? In other words, something like that. Let's say that non-zero. That is normalized. This is with the binary, presumably base of 2, and the leading bit is 1. Then you might reasonably ask me the question, well, why don't I just say the leading bit of 1? I don't, because we also can have a base of 16, right? Yeah.
In the base of 16, would you have hexadecimal notation?
Well, that's hex.
Okay.
That is in effect hex. It's simply that, you know, we won't be writing ABC, whatever, we will be just using the binary because that's the way it's used. That's exactly what it is. That's right. That's a hex. Okay. Any? Go ahead. All right, so this is normalized. That is not normalized. All right? So in other words, this equals 0.1 times 2 to the minus 1. Right? You can take it into that and normalize. Right? You have to take away 1 from the exponent. Right? So we'll be now playing with the representation so that you'll be comfortable. This is the fact about the mantissa. Why do we have that? As I was explaining, that's the whole point of the scientific notation. To take in the zeros, whether they are the trailing zeros in the integers or the leading zeros in the fractions, to take them into the exponent for the economy of the representation. I'll give you some drastic examples, but you have to understand that the game here, it's not intuitive to sort of, if we come off the street and look at it, but every bit here is a tremendous price. Every single bit, whether it's 23 bits or 24 bits, you know, the numerical analyst can spend half of the life arguing which way to go, to put the bit here or to put it there. Because here you get a larger range, right? Here you give up on precision. That's a trade. That's a very big deal.
How would the system know that it's processing a floating point number?
The way it knows is strictly by the way you use it.
Okay.
Okay, in other words,
Operand.
you use the operations that are floating point operations. Okay?
So if you were to misuse it, it would be misunderstood.
If you misuse it, you'll be in trouble. That's right. That's exactly right. I say you have to use, let's say, floating point addition versus addition. Okay. The second fact. And you know, there are only 2 facts, but you have to really take them in. Right? the exponent is biased. In other words, that's what we did here. The volume of 2 to the n minus 1, but this is n in this case, is added to each exponent. And the argument is, in order to make it non-negative, and that is, again, why in order, second order, to compare the exponents, let's say in addition, during addition. Addition is a harder operation for floating point than multiplication. In multiplication, we add the exponents. In addition, the exponents have to be equal. In order for them to be equal, one number has to be denormalized. And the only way we can live is that we have to denormalize the smaller number, because in that case we have to shift the mantissa to the right, introducing the leading zeros. Because if we shift the greater mantissa to the left, we lose the most significant bits. We cannot do that.
You lose some precision when you do that.
Well, we lose the precision, that's right. We will be talking about that. The precision, numerical analysis is a science. And the people who do that have to be familiar with how the precision can be lost and how to restore the precision. And this is not our brief here, but those two things we have to understand. Okay, so let me give you an example. Okay, let's see how that works. Let's take a number, a good live number, and let's represent it in floating point. Mistakes here. Let's say convert to floating point. And remember, so that we don't have any dissension here, we use that representation. 7, 24, and 1. Okay? Don't get confused with the book, because as I said, in order to be realistic, we have to have a hidden 1, and that makes it unreadable. Yeah?
Do you mean 1, 7, 24?
Yeah.
7, 24, 1.
1, 7, 24. That's what I wanted to say. And said that I shouldn't. Right? To the floating point representation. Okay, so the procedures 1, convert to binary. Obviously, right? Any questions? Right?
No, I'm fine, thank you.
Okay, anyone else?
Yeah, please.
If you got the question, in my experience, if one person has a question, at least 3 other people have the same question. Right? So if you have a question, just ask.
Thank you.
That's why I'm here. Okay, so we have 128. Right, and 64, 128, 64, and this is 192, right, and we need still a 32 won't come into that, and we need 16, so we have 208, and then we need 7. I hope it's okay. Seems all right. And then check it out, see whether I haven't made any mistakes. Okay, now we have to normalize. That's the procedure. Okay, in other words, we have to make it into a fraction with non-negative, in this case 1, leading digit, right? So we have to shift it right. In this case, if the number were less than 0, we would shift it left. Right? So we obviously right? Of course, this is not the same number. Times, we shifted it 3, 6, 8, 2 to the 8th. Okay? Is everyone comfortable? If you are not comfortable, just type up. It's now a normalized number, right? That will be our mantissa, and that will not be our base. Why? Not our exponent. Why? We have to what?
Assign it.
No. We have to bias it, right? We have to bias it, right? Okay, so I don't want to sort of mangle that number. The exponent equals 8 plus 2 to the power of 7 minus 1 equals 8 plus 2 to the 6 equals 64. That is the bias in our case, and that will always stay there. In other words, with 7 bits, 2 to the power of 7 minus 1 is 64. That's our bias. Always, right? So that's the
Wait,
way.
how did you get 7?
7 is that, the length of the exponent. Okay. Right? So we can represent the numbers of what? Well, you will see the range, but from minus 64 to 63 in the field of the exponent. Right? In other words, from 0 to 127. All goes there. Jordan,
I'm just trying, in
Yeah.
my brain. I like
that's the only place to do it.
I'm trying. I'm just trying to like compare it to something you're more familiar with, which is, you know, scientific notation with base 10. You know, so I'm trying to like, I get it up till
You know,
I
to
guess
be honest with you, that's where it's, you know, that's why it breaks down for you, the intuition. Because in your brain, you don't use biasing for scientific notation. You know, unless you do something very perverse in your, not perverted, just perverse in your brain, you know, you don't bias the numbers.
Yeah.
Right? That's why I said it's applied to the machine representation.
Yeah, that's why obviously the bias.
Up to
part
here,
is-
it's okay.
Yeah.
This
That's
is
weird.
different. That's okay. All right.
So now it's 2 to the 64th?
Right. So the number man, here we go. This is our sign. This is our exponent. This is the mantissa. And you know, sometimes when you see the machines that are built like 5th generation machine, you see awful things because you can see in double precision, I'll be talking about double precision, piece of the mantissa here, the piece there, whatever have it, which is done for the backward compatibility to the old model. So it's very, here we're trying to be pure, sign is 0 for plus. Then we have a, oh, Jesus. I meant to say 8 plus 64, which is 72. Okay? Now, again, you know, I'm not going to even add it because I know there's 64, right? This is 8. And then I just make it 70. Okay, which is 72. Okay, and then we have that number. And then this has to be completed with 0. Okay, now this is the time, go ahead, let's make a timeout, see what, you know, screen. Anyone needs to screen?
What do you mean by complete by 0?
Well, I mean, you know, there are 24 bits here. They have to be either 0 or 1. They're not 1, so there must be 0. Okay, because that is 20.
So it's left.
Right. You know, we have to be definite. Okay. Now, let me now go through a little more advanced exercise. We'll compute the range. Remember, we wanted to compute the range, and we'll compute the range with the base of 2 and the base of 16. And you will have some amazing conclusions there. And also, it gives us another opportunity to exercise with those values. I'll leave that. I'll leave this. Okay, we're working with 32 bits. This will be the base of 2. Oh, maybe I'll shift it because it takes a lot of space. Let's say this is the minimum number. And let's say this is the maximum, the largest number. And we are looking at the absolute values. We don't care about the sign, right? Because again, the sign is 0 for plus, 1 for minus. Okay. Now, to begin with, what would the smallest number look like? Okay, in other words, subject to those conditions.
1.
Okay, so the sign can be 0, 1, we don't care. Then what is the smallest possible biased exponent? Yeah? 0. That's right. Can't get any smaller. 0. We don't have negative.
So that would be if you had 2 to the 6th power exponent already there. A negative
This is negative 2 to the, in other words, the real exponent is minus 64. You add 64, that's what happens here. Can't be any smaller than that.
And that would be in the 2's complement form?
No, there's no 2's complement. It's all straight numbers. No 2's complement, that's the same. Nothing is in 2's
So
complement.
the sign in this case.
The sign is sign magnitude. The sign does not apply to the exponent. The sign is that of the number.
And how do you distinguish between positive and negative exponents?
That's where the bias comes in. If I take off 64, that's well down negative, 2 to the minus 64, right? So anything like that, right? Anything, in other words, that doesn't have 1 in here is a negative exponent, in fact.
Oh, okay.
It's an artifact of the
And
representation.
that's why you have the -1 is for
That's
the
right.
sign.
That's why we don't have a sign. We have only one sign. Remember, we don't have, that's the sign of the number, not the sign of the exponent. The sign of the exponent is eaten up into the bias. Yeah, as I said, it's all very simple, but yet, you know, it's a hurdle. So I want us to get over that. Okay, and what's the smallest normalized mantissa fraction? As small as it can get.
All zeros. All zeros.
Is it normalized?
1,
Yeah. And?
all zeros.
Yeah, all right. I'm buying that. Okay. 1 and then 1, 2, 3 zeros. So, okay.
All the confidence of that.
So, all right. Okay, remember it has to be normalized. There's a special value that is all zeros, and that is an absolute 0. And that value is a special one that belongs to the representation, but again, we are not talking about that now. I'll show you the number axis. And I want you for now to also keep digesting, someplace in the background, the fact that with the floating numbers, we live in sin. With integers, we live in truth. With floating point numbers, we're always lying a little. I mean, with some exceptions. A floating point number, a real number is always an approximation. I mean, always is not true. But let's say if you throw a brick at a number, it's probably what?
High probability.
Extremely high probability. This is an approximation, right? Because we are trying to represent remember, real numbers have infinite length. And we are trying to squeeze it into a finite box. 24 bits of significance. Right? So there you have it. Now what have we here? Plus or minus. Right? This is what? Let's write the exponent with the mantissa first. What's that? What's the value of this? As a power of 2. No calculators. You don't need a calculator for that. It's more trouble than it's worth.
Adding rules.
Nothing, no slide rules either. Have you ever seen a slide rule?
Yes, I have.
Where?
My father had one.
Ah, your father had that. That's okay. So you had a special, I had to work with the slide rules. Yeah, Jesus. I mentioned, oh God, should have been mentioned. Okay, now what?
16 megabytes?
What megabytes? Who is the megabyte?
I don't know, you wanted it without
What is the megabyte?
2 to the 24.
We are not talking about the memory here.
I was just trying to make it less
Just
big sounding.
You're trying to scare me, all right. 2 to the minus 1, how about that? Because that's a fraction, right? So in other words, all that's said here is this. And that's what it said, right? Here. It is a fraction with a leading non-zero digit. In the case of binary representation, it's with a leading bit of 1, which is what you got. And that's what it is. And that is 2 to the power minus 1. Okay, now if anyone doesn't see it, just pipe up. I'm not rushing across what you
Just do it
understand.
one more time? Say it one more time.
All right, look. This is the row,
Yeah,
okay? Now I'm throwing at you that number.
yeah.
And I'm saying, look, that is a fraction with a leading non-zero digit, but anyway, you know that.
Yeah.
All I'm saying is this is a binary fraction. This is 1 with 10,000 zeros if you want. Who cares? 23 in the event, right? So in other words, this is 1, and that's what we had there. This little
yeah.
thing, right? The whole fact, 2 to the minus 1, half in decimal.
My bad. I forgot that it was after the decimal place.
After the decimal, it's a fraction, right? That's what
Yeah.
we have that fraction. Okay.
How would that be the smallest number?
Well, can you come up with a smaller number?
Well,
Show me the smaller number.
it's
Why can't you put the 1 all the way back?
It has to be normalized. Normalized.
But you also have a negative 64 exponent in front of it.
Yeah, well, that too.
So
But he
you have
wants to
64
do,
zeros, or
he
63
wants to
zeros
do
there.
that, but that's not normalized.
It's not number.
It's left just.
So we cannot have it. And it has to be normalized because we have to have a unique representation for each number, and we want to use our motivation is always there. The main thing in this course, in any course, should be motivation. Why? The why is that we want to use the whole 24 bits, right? Because it's not very likely that a number like that will come down the pipe, right? They usually don't come like that. The number will come with 24 zeros and ones, and we want to use the whole space. Too nice?
Yes.
You comfy?
Yes.
It's a small class, everyone can be comfortable. That's step 1. Okay, so we have that, we're not done. And then we said this is what? Right, because we have to take back this 2 to the minus 65. Okay. next? Let's leave presumably the 16 to one side for now. And let's look at the maximum number to compare. Again, absolute value 0, 1. Well, I mean, it can't get any bigger than all ones, right? We know that intuitively. 3, 6, 7 ones, and of course here we also have all ones. Can't do better than that. Right, so now let's see what that is. Right, let's begin with that because that's simple, and this is what?
265.
Be careful.
Oh, 64.
Be careful.
128.
Don't give up. It's just a be careful. Oh, you're on the right track.
Positive 64.
Okay. The value is, 127 is what you see. You have to take out the bias, which is 64, you're left with 63. Okay, so we got 2 to the 63. I could give you the general formulas, but it's not worth it. It will just poison your life. Now, there's more here. A little more to talk about here. All right, what is that number?
24 ones.
But they're all fractions, right? In other words, what we have here is something like that. Actually, very much like that. Actually, there's 24 ones. Now, what's the value of that?
All the ones.
What?
Has all the ones.
Well, no, but what's the as good as what? Yeah.
I'm fine.
I mean, if I locked you up and said, well, give me an approximate value of that. You don't come out of the room until you give me the value of that number. And you would be forced to really come up with that. What would you come up with?
2 to the negative 24.
This is the binary fraction. Okay, so let's go through the inductive proof. Since you didn't behave, let me give you the inductive proof of that. Right? It's simple. Right? Let's say this is 0.1. Let's keep increasing the number of bits. Right? What is the rule for that, and so on? Right? This is 1 minus 2 to the negative power. This is minus n, depending how many bits. Right? If you have 3 bits, you take out 1/8. If you have 2 bits, you take out 1/4. If you have 1 bit, you take out 1/2. Right? So in this case, this is 1 minus 2. In order for you not to get confused with any other numbers, let's say I'll call this m, and that's the length of the mantissa. In fact, I call it proper. And 1 minus 2 to the minus 24 times that. Right? In other words, to a human being, this is as good as what? That?
1.
1, exactly right. This is as good as 1. In other words, it equals just about 2 to the power 60. Check it out. Because that is a vanishing number, right? It's a very small number. It's 1 over 2 to the power 24. Right? 16, whatever, billion something. I mean, but it's binary. Yeah, by the way, what is that in human? In other words, if we want to, ballpark value, what do we have here? How big is the number? I said we have a huge dynamic range. What is it approximately in decimal? Right? Well, 10, 8 is 2 to the power of 3, so we would have to divide it by 3. Right? we have to divide it by more than 3. And as it happens, in this case, if we have to divide it by more than 3, we have to divide it by 3.4, and that gets you about 10 to the minus 18. Right? In other words, you got 18 decimal zeros. So it is a very small number. It's not good enough to work with the accelerator in CERN, but it's a small number.
How did you come up with 3.4? Is that just like a given, or?
3.4 is a God-given, in other words, approximately, the power of 8, if we wanted to convert it to the octal, I would have to divide it by 3, right? So that's why we have 8 to the power of, let's say, 22, right? 10 is a little more, and I happen to know that that's 3.4. In other words, I didn't discover that fact. It was done before the academic clinic. So that's pretty much what it is. That's fine. And then this is also something like that. Yeah? So you have 36 digits, decimal either way. So you have, this tells you about the huge dynamic range. You have to understand the meaning behind it, not the number. That is positive, thank you very much. Good. Otherwise, you don't have any kind of
Maybe convert 10 to
number.
0.
Right? Not very impressive. But you see the range, 36 zeros span. That is the huge dynamic range, which is nothing as compared to base of 16. You will see it. Yes, the base of 16. Okay. The minimum number. Well, there's no reason for that to be any different. Yeah? Whether it's 16 or 64. Right? What is the minimum number according to the rules? Normalized Mantis.